Welcome to Unit 3, Lesson 8. As usual, you're going to look for the tasks for U3L8. Should be under assignments or on the weekly calendar at today's date. Today is the 4th of December. Happy Friday. Our goal today is to wrap up our phase changes and states of matter with a fun little kind of video quiz. And then we're going to introduce gas laws and hopefully get through the first gas law today. But we'll start off with the usual chat in breakout rooms. The question for today is in the chat now. It's what's your favorite place you've ever visited? What's your favorite place you've ever visited? Think about that for 20 seconds. Also, don't forget to say hi and check in with the person you're in the room with. We'll come back together in about 2 minutes. Rooms are open. It was a little bit of homework review. All you had was the Ed puzzle and making sure that you completed the classwork. Classwork was looking good. Ed puzzle also, I'm seeing 29 attempts for some reason. I think another class might have taken the same one. But let's just take a quick look at the demonstration I gave you. So I was in the science building at sea level. The reason it didn't boil at 80 degrees Celsius, most of you got it, is that at sea level, you have to get to 100 degrees Celsius in order for the vapor pressure of water to match the atmospheric pressure and boil. The machine making that funny sound, sucking air out, and that's going to decrease the air pressure or the atmospheric pressure inside of that glass container. Looks like we had to struggle with that one. Everyone thought it was increasing the pressure. That is not the case. It is decreasing the pressure. Why is water in the beaker now boiling? So again, if I decrease the air pressure inside of the little glass container, that means that it is coming down and equaling the vapor pressure of the water, even though the water is only at 80 degrees Celsius. And so the water begins to boil because, again, you've got to memorize that definition of boiling point. It's when vapor pressure equals atmospheric pressure. And so by bringing atmospheric pressure down, it was able to boil at 80 degrees Celsius because that was when it matched the vapor pressure. And if I want to do the same activity without using a dome or a vacuum machine, where would I need to go? I would need to go to a much higher elevation like Mount Everest. Again, looks like most of you got that. Okay, any questions or comments on that particular homework assignment? I guess the Ed puzzle doesn't let you retry the questions, does it?
No.
It doesn't. Have you done, I haven't messed with the Ed puzzle settings. Like, have you guys done Ed puzzle in other classes where you are able to retry the questions, or has it always been one try? Always been one try? Okay, all right. So I guess there's no setting. I was wondering if there's some setting I could change, but okay, again, don't panic if you got a lot of stuff wrong. I'm gonna be grading for completion. That's the main thing, not correctness. But again, always feel free to rewatch it. There's gotta be a way that I could set it where it won't let you advance without getting it right. I'm curious about that, but anyway, I'll mess around with that later. We are going to be doing a few other Ed puzzles today. Okay, first thing you're going to tackle is our last thing we're going to do with phase changes. We are on tasks to complete step number 3, atmospheric pressure can crush. And so click on the assignment right there, atmospheric pressure can crush classwork, and it'll take you to a quiz that looks like this. I've got an embedded video at the start, as well as some instructions. And actually, I'm just gonna go ahead and we'll watch the video together here all at once. Optimize my screen. Here we go.
Hi, Science 2 kiddos. Gonna use this video as a demonstration of what's called the atmospheric pressure can crush. Now, you can either just watch this video, or an optional alternative is you can try this at home. However, you do not have to. This is a little bit dangerous. But I'll walk you through what you need. Safety is going to be the most important thing, so you need some kind of eye protection, glasses or sunglasses. I've got my lab coat on and something to protect your hands. You're working with boiling water. That's the main thing that's dangerous, as well as a hot surface, so oven mitts or something are good too. Let's do some science. Now, what you're going to need if you do try this at home is an empty aluminum can, as I mentioned with the homework. You'll need a bowl with some water in it, just regular sink water, and it doesn't have to be glass. Glass just makes things more visible. And so you're going to fill the glass bowl with water from the sink. You need to fill the can about a quarter full of water. You really don't need that much. I mean, I would use about this much or so and just pour it on in there, like so. And you're going to need tongs to grab this can, because what you're going to be doing, as you can see over here, is heating the water in the can on a stovetop. And you'll want to keep it going until you hear that I'm not sure if it's coming through in the video, but you can kind of hear it bubbling in there. And there's a, you can see the water vapor coming out of the opening on the top here. So then what you're going to want to do is use tongs, again, because you're going to grab the edge of the can here, like so. And what you're going to do is you're going to invert it upside down into the water. So you want the opening on the top to go into the water. Okay, so that's what I'm going to do. Again, be very careful if you're trying this at home. You don't have to do this at home. You can just watch this video to answer the questions. But if you want to give it a try, have some adult supervision, someone to help you, and just make sure you're being safe. Keep your distance. So watch what happens when I now take this can that has boiling water in it and place it in the water. Here we go. Now, you'll notice the can imploded. And that wasn't me squishing it with the tongs. That was something else going on there. And so the question you'll need to answer as part of the Canvas quiz you're working on is why that happens. So again, please answer the questions in the quiz. If you're going to try this.
Okay, we're going to stop there. Pretty cool. What I'm curious about is how many have you, show of hands, have seen this before? A can implode when it's put upside down. Has anyone seen this? Tristan? Okay, it's kind of a fun, very common scientific experiment. So isn't that cool? The can literally went, and that wasn't me. Again, that wasn't me squeezing with the tongs or anything like that. There's something going on with phase changes there, which is really cool. So what I'm going to do is time for 20 minutes. You have 20 minutes to work through the quiz. The quiz includes, I think, like 2 questions, and there's 2 ed puzzles that are embedded in it that you can go do and then just say, I did the ed puzzle and move on, or you can watch the video on YouTube, all of which will explain this, and we'll kind of review it when we come back together. Again, if you want to try this at home, you can. So just follow the instructions that I have on there. That's not a required assignment. It's not graded. You don't have to do this. There is a bit of danger involved, and so I don't want to encourage it too much. So it's up to you. If you want to give it a try, you can take some time to do it right now too, and then come back to the ed puzzles later. But either way, in 20 minutes, I want us all to come back together to review. I'll be here listening as usual if you have questions or need help on something. Go for it. 20 minutes to work on the can crush classwork. Sort of classwork quiz that I'd like you to follow along with. So we're on the last step here, step 4, intro to gas laws. I encourage you to open the slides if you want, just to have those to refer to. But what I'm going to do is go over those by sharing my screen with my iPad like I've been doing. But then we're going to kind of take some pause moments where you're going to work on this classwork quiz. So go ahead and open this quiz up. It's like any other classwork quiz we've done. You have up to 10 attempts to complete it. I'm hoping we'll get through all of it, but we might not. We'll see. Again, this is my first time doing this, so we'll see how quickly or how slowly we go. So if you click on the classwork quiz, it will take you to something that looks like this. And you'll see there's just a bunch of blanks to fill in, and I will prompt you when to work on those things, and we'll review them and come back to them. So go ahead and open that quiz up, and I'm going to pull up my iPad to introduce you all to what are called gas laws. And let's see how far we get. Okay, where did notability go? All right, can I just get a verbal confirmation? Everyone's seeing nature of gases in front of them?
Yeah.
All righty, here we go. So we've been learning about the states of matter. We're going to focus on gases because they have a lot of cool things going on with pressure and just their behavior. So there's a couple assumptions we're going to make here, right? We're going to assume that gases are composed of tiny, small particles. So think of those as like oxygen molecules or nitrogen molecules or helium molecules, which is what air is mostly made out of, right? Gas particles are constantly moving. So we saw that PhET simulation, the link is right here, but you saw that where things were just kind of bouncing around constantly, right? That's what gas molecules are doing. And we can assume that they bounce off each other with equal energy. You often hear this as elastic collisions, which just means that if you have 2 gas molecules that smack into each other, they're going to shoot off with equal amounts of energy, right? There's no change. They don't stop. They don't merge together. They just bounce off of each other. Exactly what that animation showed. This is the source of gas pressure. So we've been talking about atmospheric pressure, air pressure. All that is these little tiny gas particles colliding with something. You can feel this in the air just by waving your hand around, right? You can feel the wind around you. That's because you're smacking all those air molecules around. It's not necessarily the same thing as pressure, though, but the amount of pressure we're under is because we have all these air molecules around us and weighing on top of us as well. So the tool that we use to measure air pressure, and I don't know if anyone pays attention to the weather, or you might have one of these outside your house at home, but they're called a barometer. And it just tells you what the air pressure is doing. And not surprisingly, you can make predictions about the weather, right? Lower pressures tend to mean that you've got rain coming or something like that, right? And higher pressures means you've got warmer days, nicer weather on the way. But it's just a device used to measure how much air is sort of weighing down on us, right? What's the overall gas pressure around you in the atmosphere? And it's kind of cool the way it works. I'll show you in a second. But first, we need to talk about what are the units, right? Everyone knows we use meters for distance and Celsius for temperature. The SI unit for pressure is called a kilopascal, kPa. Other common units, though, what we use in the United States is pounds per square inch, right? So if you're talking about the, how inflated a football is or a basketball, that's PSI. If you remember the Deflate Gate with the Patriots recently, PSI was all over the news. There's millimeters of mercury and atmosphere, and I'll explain what's going on with millimeters of mercury in a second. But the first thing I'd like you to do on the quiz, so if you open up your quiz, the first question asks you to fill in the blanks in the conversion. So go ahead and fill those in. It's 1 atmosphere is equal to 760 millimeters of mercury, equals 101.3 kilopascals, which equals 14.7 psi. Those are the equivalencies, which are going to allow us to convert between them. So go ahead and enter those in the blank. Just verbally, real quick, again, don't be embarrassed. Is anyone not sure where to find those blanks to enter them? Everyone see where we are in the classwork? All right, I'm assuming we're good. Again, if you open up the slides, you can find this same slide if you're feeling behind. Okay, what the heck is going on with millimeters of mercury? Why is that? Isn't millimeters a distance measurement? And the answer is actually, yes, it is. It's based on early barometers, which were literally just liquid mercury, so liquid metal, that was inside a dish, and they inverted a little test tube. So this is open on the bottom. You can't see it, but there's a little opening down there. And so as atmospheric pressure presses down on that mercury, right? So the amount of air pressure, depending on whether it's high or low, presses on that mercury, and it pushes it up this test tube. And so we can then just put a scale on there, and that's what we're measuring is how many millimeters up or down is the mercury at that time. And it's set to come some kind of standard. I don't know exactly what, but that's something we'll explore a little bit later in terms of what's going on with that. And you've got a vacuum in here, so there's very little air inside influencing the inside of it, right? We're just trying to measure the atmospheric pressure outside. Okay, all of this has been building up to what we call the gas laws. This is what we're going to be spending the next few lessons on, most likely. And that's looking at 4 variables. There are 4 things that we can describe about gases. The first is pressure, which we were just talking about, right? We can measure it in a variety of different ways. The second is the temperature of gases. We can warm up or cool down gases. We can also measure volume, right? How much space does a gas take up? This is usually measured in milliliters or liters. Temperature, I should mention, is measured in Celsius, but the more scientific unit for temperature is K. Anyone want to jump in and tell me what K stands for?
Kelvin.
Very good. That's the SI unit of temperature, Kelvin. To convert between Kelvin and there, you can just note this. I'll always provide this equation to you, but you just add 273 to whatever your degree Celsius is, and that will tell you the Kelvin. And then there's also moles. We're not going to spend a whole lot of time on moles because it's a pretty complicated topic, and it's something I believe you explored in PSI last year. So don't worry too much about that. Our focus is going to be these first 3. What are the relationships between pressure, temperature, and volume? So specifically, what I want to find out is like what happens when you change one, right? What would happen if we were to increase the pressure? What happens to temperature? What happens to volume? And so on. And it turns out that these have relationships That's what the gas laws are. It explains the relationships between pressure, temperature, and volume of a gas. But before we delve into that, we got to talk a little bit about unit conversions, because I'm going to try to mess with you a little bit here. I'm not always going to give you matching measurements. And so you need to be familiar with the idea of using ratios of equivalencies to convert from one unit to another. So what I want to explain here is, does everyone see I've got two metal rulers here that are exactly the same length? I'm hoping we can all agree on that. If everyone looks, they're exactly the same length. This one, though, is measured as 100 centimeters, and this one's measured as 1 meter. I can set that up as a fraction to show that relationship, right? 1 meter is equal to 100 centimeters, or I could invert it and say that 100 centimeters is the same as 1 meter, right? Those are the same thing. This is going to be what we call a conversion unit. So let me give you an example. Here's another equivalency, right? Everyone knows that there are 4 quarters for every $1, right? $1 in the US is equal to 4 quarters. So the reason something like this is useful, and again, I can invert it. I could also say that I can say that $1 is equal to 4 quarters. $1, same as 4 quarters. Doesn't matter what's on top or what's on the bottom right now. But let's go ahead and pick an arbitrary number. What if I had 10 quarters? And I wanted to know how many dollars I had, right? Now, yes, you could do the math in your head really quickly, but I want you to get used to writing out an equation where here's what you do. You multiply by a fraction, and what you do is on the bottom, you put your same units. So let me move this over so that we have a better view of what's going on here. I don't even remember what I said now. Was it 12 quarters? 12 quarters? Let's just say how many dollars are in 12 quarters. So you're going to multiply by a fraction. You're going to put quarters on the bottom. You're going to put dollars on top. We know the relationship is $1 is equal to 4 quarters, right? We got that from this. That's always the relationship. And the reason we do this is because anyone know if I've got quarters on top and quarters on the bottom, what are those two units going to do to each other?
Cancel each other out.
Cancel out. And all we're left with is $. So then all you got to do is do 12 times 1, which is 12, divided by 4. Anyone know what 12 divided by 4 is?
3.
$3. So if you have 12 quarters, it's $3. So again, I know some of you are like, well, I could do that in my head, no problem. But I want you to get used to this idea of converting, because we're going to start doing stuff that you can't necessarily do in your head, specifically with pressures. So I just told you that relationship of all the different pressures. So now I'd like you to try using that to convert these example problems. Oh, and I forgot to include the Kelvin conversion here, but just remember that to get Kelvin, you just take your degrees Celsius and you add 273. So you have these exact same questions on the classwork quiz that you should have open. I'm going to just do this first one as a quick example, and then I'll let you do the rest on your own. You can do the work in the notebook and then just type in your answers on the Canvas quiz. So we've got 2.5 atmospheres. I want to convert that into kilopascals. So I know I'm going to multiply by a fraction. I'm going to put atmospheres on the bottom so that those cancel out, right? I want to cancel atmospheres. I want to get kilopascals, so I'm going to put kilopascals on top. I need to find that relationship. What's the relationship between kilopascals and atmospheres? And so look up here. I know that 1 atmosphere is equal to 101.3 kilopascals. Does everyone see that? That's the equivalency. So I put 101.3 on top, and I put 1 on the bottom, right? 1 atmosphere is the same as 101.3 kilopascals. And then you just do 2.5 times 101.3 divided by 1. And I forget what number that gives you. It gives you 253.3 kilopascals, because that's the unit that's left over. All right, go ahead and try some of those other conversions and enter the numbers into the Canvas quiz. All right, kiddos, in the interest of time, let's move on. Just showing you on my screen here how to solve these other ones. So 73 degrees Celsius to Kelvin, all you have to do is take 73 and add 273. Same thing over here, 500 degrees Celsius to Kelvin, you just take 500 and add 273. That's the equation for the conversion. For letter B, you're going to take your 511 millimeters mercury, multiply by a fraction with atmospheres on top, because that's what you want to get, and millimeters mercury on the bottom. And we know that relationship is 1 atmosphere is equal to 760 millimeters mercury. So 760 on the bottom. Millimeters of mercury cancel out. You do 511 times 1 divided by 760. You should get a small number, 0 point something. Here are the answers that you hopefully got. Looks like 0.672, 346, 773. You can check yourself using the slides as well. Any questions or concerns on that so far? We'll get more practice. Okay. Let's talk about our very first gas law, Boyle's law, named after its discoverer, though I think earlier kind of observations about this were present, but it's just a mathematical equation. So here's what Boyle's law states. Pressure is inversely proportional to volume. Not surprising, right? That means that if you increase the pressure on something, you are going to shrink it down. You're going to decrease the volume. So in other words, if pressure goes up, then volume goes down. Vice versa is also true. As you are hopefully probably aware, if you decrease the pressure of something, you can then also increase its volume. Think about Bob Gardner's balloon, right? When Bob Gardner's balloon was rising up through the atmosphere, pressure was decreasing and its volume began to increase. The way this is expressed mathematically is P1V1 is equal to P2V2. And we're going to assume that pressure is in any one of these units as long as they're the same, right? So just P1 has to match P2 in terms of its units. Volume can be milliliters or liters. Again, they just have to match. And notice we are ignoring temperature and we're ignoring moles. So we can assume that these stay the same. There's no change in temperature and there's no change in the amount of gas we have. That's what moles are, is the amount of gas. So just get that equation down as Boyle's law. P1V1 equals P2V2, pressure goes up, volume goes down, vice versa. That's a good way to double check yourself. So let's do some practice problems now using this equation. You have this same practice problem on your quiz. I think this is number 1, practice 1. If a balloon filled with 425 milliliters of helium gas, there's a volume right there. I'm going to go ahead and label that V1. It's a good habit to get into. It's kept at a pressure of 101.3 kilopascal. So let's go ahead and call that P1. So we've got our initial volume and our initial temperature. If the balloon floats away, reaches a high altitude, changing the pressure to 472 kPa, so I'm going to call that P2, that's our new pressure. What is the volume of the balloon at this point? V2. So what we don't know is the aftermath volume. What is the second volume? How did the volume change? Now, I'm hoping that you can already make a prediction here. Can anyone tell me what happened to the pressure? Did the pressure go up or go down from P1 to P2? Did it increase or decrease?
Decreased.
It decreased. So can anyone make a prediction then? Based on Boyle's law, remember Boyle said that they are inversely related. So if pressure is going to go down, what are we going to expect volume to do?
Go up.
Volume should go up. So our answer should be higher than 425. So then all you got to do, it depends on how you feel about algebra. I know some people rearrange the equation to solve and then solve, or you can just plug in the numbers. I like to plug in the numbers just because I think it's more straightforward. Rather than wasting time writing it on the screen, here is how you should set up your answer. So see how I plugged in P1 and V1. So 101.3 times 425 is equal to P2 times our unknown. We don't know V2. So then you just divide both sides. So what I did was I brought this over, right? Brought it under the 101.3 kilopascals of 425. So I know that's going to equal V2. So all you got to do is 101.3 times 425 divided by 47.2, get V2 on its own. You should get something like 912 liters. again, what some people do, I know, is just take the equation. So P1, V1 equal to P2, V2, and do the same thing where we just need to divide both sides by P2 to remove, or by pressure. I guess, yeah, it's confusing with the P1, V1 thing. So let's just say, yeah, that we're gonna move P2 over here. We gotta divide by that. And so that's why you end up with V2 is equal to P1 times V1 over P2. So that's sort of the rearranged equation if you want to use that. That's exactly what I did here, just with numbers plugged in rather than the variables. So whatever method works for you. All right, there is a second problem that I would like you to try. Once again, on the slides, the answer is provided, but I think it's best to kind of give it a go and enter the answer as best you can on the quiz itself. All right, questions or comments on that? All right. There are 3 laws we're going to learn in total: Boyle's law, Charles' law, and Gay-Lussac's law. But I'm going to try to slow down and just make sure we're feeling comfortable with the math and stuff too. The homework I have not actually been able to enter, but the homework will be actually another ed puzzle with some associated math questions in a quiz. I'm still putting it together though. So again, that will be done by the end of today or shortly thereafter. So, all right, kiddos. Thanks for bearing with me. Hope you enjoy the weekend. Stay safe out there. Thanks. Bye.
Thank you.
Thank you.
Thank you.